Hi guys, welcome to the fifth, I believe, session in our little paper of the week for MDE. For this week we decided to go back to English, paper that I've read a little while ago that I thought was quite interesting. So the name of the paper is an EMF-like UML generator for C++. So it shares some of the ideas of Dogen in the sense that we are also targeting the code generation for C++. We also would like to create sort of a model sort of a generator that uses a C++ model to generate C++ code, that kind of thing. It uses EMF, so it's more of a standard MDA or MG kind of tool, rather than our bespoke approach. So it ticks all the boxes basically. So let's have a quick look at it then. So let's start with the abstract. Actually, let's have a look at the keywords. So model-based software development code. Another interesting point is this is a 2016 paper, I believe. So it's fairly recent compared to the papers we tend to read around here. So model-based software development, code generation, meta-modeling, C++, UML, MOF, and eCore. eCore being, of course, a technology developed in the Eclipse, I guess, for implementing UML and MOF and that kind of thing. So model-driven architecture is a well-known approach for the development of complex software systems. The most famous toolchain is provided for Eclipse, or by Eclipse with the tools of the Eclipse modeling projects. Like Eclipse itself, the tools are based on Java. However, there are a number of legacy software packages written in C++, which are often used only in implicit... okay, so this is an important point. There are numerous legacy software packages written in C++ which often use only an implicit metamodel. A real C++ implementation of this metamodel will be necessary instead to use at runtime. Right, so here we're trying to really establish that the focus of these chaps is to obtain sort of runtime aspects of EMF. We don't really we want to hide the fact that you're using code generation. These guys want to follow the usual EMF approach of actually trying to sort of make a seamless integration between runtime, generation time, everything, which is an interesting approach, but it's not what we're trying to do. I mean, it's not necessarily the case we don't want to do it. We would just like to have an option, as with everything in C++. So for us, EMF for CPP is actually a really interesting thing. It will be another target for Dogen rather than the key thing. So this paper presents a generator for C++ to create the classes, meta model packages, and factories to realize modeling transformation, validation, and comparison of UML models. Okay. Also sounds quite interesting. It's perhaps a green. See if the color changes is more successful today. Seems to always take 2 goes. There you go. It gives an overview of its workflow and major challenges. Moreover, a comparison between Java and C++ implementation is given considering different benchmarks. Okay, semi-points of interest. So perhaps it's worthwhile putting a quick note here. Objectives maybe. And in the objectives you want to say target legacy systems that have been written in C++ and therefore can't easily, I think I'm in Portuguese, so can't easily, let's put autofill mode on, make use of EMF. Provides, well, let's not make too many assumptions here. That's probably enough for now. So let's rattle through the introduction then. The model-driven architecture approach, as defined by the Object Management Group, the OMG, is a well-known family of standards which unifies every step of the development of an application, from platform-independent model to the platform-specific model to generate the code and deployable application. Okay. I'm not entirely sure what we should highlight here. Presumably the fact that we try to unify everything, I guess. Let's put a note here. So one of OMG's goals is to unify every step of the development process. Keep forgetting I've updated this to use company mode. From requirements gathering to deployment. We should make clear which parts of the development process we are aiming to automate. So our goals are not quite as ambitious as OMG's, as you can imagine. The Common Eclipse Modeling Project, EMP, supports this approach by providing a unified set of modeling frameworks, tool support, and standard implementations based on Eclipse modeling framework. It uses eCore, a Metamodel, which is similar to the essential meta object facility, the EMOF, for describing a metamodel. The EMF framework with this code generation facility can be used to build tools in other applications based on a structured data model, like complete editors for eCore-based domain-specific metamodels. It produces Java classes for the model and other necessary utilities to create and edit such a model. Therefore, the MDE approach is well integrated with the Java programming language, but is weakly supported for other programming languages such as C++. So another really important point here. I think this is probably a red. So what we're trying to say here is that for those that want to use languages, so Java is the only first class citizen of EMF. EMF is great for those in Java, but it does not aim to provide support outside of this environment. Something like this. C++ is one of the most commonly used programming languages, according to the TOEOB index. Numerous legacy software packages are written in C++ and often used only an implicit metamodel. This is a classic case. This is what pretty much everyone does. To use a real metamodel at runtime, an implementation of the metamodel in C++ will be necessary. Interesting to know what this Jungle Blood has to say for himself. Let's have a quick look. Presumably he's one of the authors, I guess. It isn't. So let's have a look at Jungle Blood. Some interesting surname. Jungle Blood, I guess. MOF compliant fundamentals for multi-domain system model in simulation. Okay. I think this is probably worthwhile. Keep it in mind. Let's add a note on geography. Interesting papers. Let's just leave it here. Doesn't seem like it's a freebie, so probably won't be able to get our hands on it, but nonetheless, we'll leave it there. Such a C++ metamodel could be used, for instance, to configure dialog properties at runtime, to realize a runtime object constraint language for checking the model elements, or to execute a behavior which is described by activity diagrams. So there's quite a few uses for runtime. I mean, this really is not our kind of thing, but we'll leave it highlighted there. There are many possibilities to create such a metamodel representation. The obvious one is to write code and implement every class manually. When the number of elements in a model increases, however, the best way to overcome the implementation is to use generator. Of course, this is why we are in MDE in the first place. A big advantage of a generator, besides saving implementation time, is the deterministic result for the transformation. Each model element is transformed in the same way, produces similar code blocks. By using guidelines like MISRA C++ for the generator, the resulting code can be used in safety critical software. Well, this is just the usual. Why do we use model-driven engineering? EMF for CPP is available. Implementation is an available implementation of the C++ eCore Metamodel, and it comes with a generator for eCore to C++ transformation. Okay, so this is the guys that have come before, and we've heard about this project as well. Just to be clear, this is another the paper we're reading at the moment is different implementation from this one, the proposed by Gonzalez in 2010. So preliminary results show that memory consumption efficiency is usually better in EMF for C++ than in Java, unsurprisingly. Unfortunately, the last feasible development activities in this project date back to 2011. So it's not very well supported. Moreover, this generator only provides the possibility to transform eCore models to C++ code. The transformation of more expressive UML is not considered. A native generator for C++ is necessary to use all capabilities of UML in describing the structure and behavior of a system, and to use the extension mechanisms of UML by defining profiles with custom stereotypes. Okay, this is a good point, and it also applies to us, I guess. Perhaps this is red too. Let's try to refresh it. Such a C++ generator has to create the classes, Metamodel packages and factories to realize modeling, transformation, validation, and comparison of UML models. Okay. Seems to have missed the S. Oh, now I missed something else. Control C, Control D. Oh, let's not delete. Okay. Alright, so if I just press Shift Delete, there we go. So we haven't quite got to grips with annotations in PDF tools, to be honest. Such as C++, we read this already. So this paper presents an EMF-like UML generator for C++, UML for CPP, aiming at a workflow and structure similar to the EMF for C++ targets. Like the EMF for CPP generator, we use Eclipse modeling project to formally describe the transformation with Acelio. Acelio is a generator tool which uses OMG's model-to-text transformation language. Interesting. Section 2 presents the workflow and the structure of the use of UML for CPP generator. Selected challenges and implementation details are presented in Section 3. The results of a comparison between the Java and C++ implementation is given in discussed Chapter 4. Finally, ongoing further work is summarized in the conclusion. Okay, so interesting points here. First, we're using a tool, probably a closed source tool, Acelio, or actually it's probably part of EMF, given it's part of the Eclipse Foundation, so that's not too bad. So, workflow and the structure, challenge with implementation, and then finally benchmarks. Okay, fine. Workflow. This section sketches the different steps which are necessary to achieve UML compliant C++ representation of a model. It's not enough to just convert the classes to C++ code. For a full featured implementation, the upper levels of model hierarchy are needed as well. So this is very important. Sadly, we can't really properly do notes across paragraphs, but we shall do it as best we can. Figure 1 depicts the structure and dependencies of the elements which are necessary. So look at figure 1. So we got some eCore model. We have UML.eCore. So eCore.eCore is the model describing eCore itself. UML.eCore is the model describing UML. This is a user model, presumably. Then we have eCore to CPP. This then generates a whole lot of C++ code, presumably. Then we have the user model. That also generates a whole lot of C++ code. They all get linked together, and out come some DLLs and the user model, and then we can then finally make use of this at runtime. So from our perspective, this eCore model, the eCore to CPP, this stop level here, we see this as a platform description model, and eCore is just yet another platform. So we probably should just write some notes on this. Workflow. So from a Dogen perspective, UML for CPP is just another PDM So platform definition model, and we could target it. It would allow us to generate MDE compliant, let's put quotes here, MDE compliant codes useful for certain scenarios. So there's nothing stopping us from making use of the work that these chaps have done already, and we could just target it as another kind of generation. However, the important bit here to keep in mind is we need to understand how to bridge the domain model objects that we generate from Dogen and the ones that are coming from eCore. So in other words, say you generated enumeration, you need to expose that enumeration into eCore. So for this we probably also need UML for C++. So we probably need, let's just go back here a little bit. So we probably need UML for C++ slash eCore specific facet, which is responsible for bridging the Dogen Metamodel elements into eCore. There would also be a need to, because of course you could easily end up in a sort of a two worlds sort of scenario where there is a metamodel description of the entities that you created with Dogen, but then if you take a factory, so if these guys here are going to, as you will see here later on in the paper, they're going to do things like providing you factories and so on. So it is possible for them to generate at runtime an instance of an object. Now, in order for that instance of that object to then bind back to the object that we generated in Dogen, we need a lot of machinery. Actually, this is probably not a good idea because to bridge the gap between the two different, excuse me, bit of a call coming, I think. So the two different representations, we would end up creating lots of glue code, of brittle glue code. We should just have two completely different kernels, the regular masked kernel and an EMF kernel. Now we've already started supporting multiple kernels. If I just quickly go up to die, I can show you what I mean. So if you take a normal Dogen model, like the logical model, actually let's go to the physical model. We have a concept of a kernel, and at the moment of course there's only the masked kernel, but there's nothing stopping us from having another kernel, the EMF kernel say. And this kernel would then have a completely different set of technical spaces and so forth. So for example, really what we should do, and we haven't done yet, is we should really name our text model after masked, because this is really an implementation of the masked kernel and this is the C++ representation of that. And so presumably we'd have an MDE one, an EMF one, which would make sense. So that's fine. So let's just go back to the paper then. It shows the 4-layered Metamodel architecture of the UML. Starting with the topmost level, the Metamodel is in our case, eCore model. The eCore model is transformed to C++ source code with the help of eCore to C++ generator written in SLEO. eCore's expressiveness is much lower than UML. Therefore, it can only describe the structure of a software system but not the behavior. Okay, fine. That's exactly what you want. We're only talking about structure anyway. The generator needs additional information concerning the semantics of the model to generate proper source code. Therefore, both the eCore.eCore and the UML.eCore models are enhanced with annotations. This is the usual method for extending eCore models with additional information. Annotations are used to specify the following aspects. So, method implementation, visibility for methods, get a set of renaming, union, subsets, ignore, C++ includes. Okay, this I think is quite important. Let's just struggling a bit here to highlight this. Seems like when I go interesting. When I go past this bit here. Not totally clear why I can't highlight this bit in one go, but there you are. So we probably want to say annotations. So eCore models are augmented by annotations. We need to understand how these differ from our variability approach and make sure our names are in line with the EMF annotation terminology. Okay. I would like to change the color of these chaps, to be honest. Seems to be quite important. Interestingly, we seem to be able to change the colors of a few of these, but not all. And there you are. So all these things can be supplied by annotations. Of course, we have our own system of annotations. We just have to make sure that the terminology and the approach is as similar as possible. By using the same Metamodel and Metamodel and Metamodel as the Eclipse modeling project, the MP tools can be used to model, transform, and validate the input of our generator. The eCore to C++ generator classes. Generator creates the C++ classes, the model factory, as well as the model package. This code is compiled to a library and can be used by the lower model levels. To create source code out of UML models, a second generator is needed. It is loosely based on the SLO generator for eCore, but does not need additional firm information except for the includes. Now it's interesting here that we have two types of generators. This is the kind of thing I don't really like. So we have a generator to generate the C++ to eCore, and now we have a generator to generate the user level code. So there you are. Let's put a note on this. To generator approach. Instead of having a single generator for both eCore and user models, there is one eCore generator and another just for user models. This is not ideal. I'd rather highlight this on red, I think, because I mean, this is a bit of a red flag, but until now, the supported features of our UML for C++ generator are class creation plus attributes, operation implementation by using UML opaque behavior. Another one to have a note. UML opaque behavior. Investigate this term. Reflection plus package factory profiles with stereotypes, constraints, activities, and actions. Okay, that seems pretty comprehensive. With these generated libraries, an application now can load an XMI representation of a model. This is used to create the M0 instances of model elements, which can be queried for properties of the upper layers depicted in Figure 2. Figure 2. The UML metamodel of the M2 layer has special property because it was described with the eCore metamodel on one hand and provides MOF-based reflection for the lower levels. On the other hand, the UML library has elements for the reflection of both metamodels. Because each model element includes the methods of the reflection from the upper layer, they can access the description of their own type. Okay, it's quite nice. In the M1 layer of a figure 2, the model class can be accessed M2 layer by using the method getMetaClass. So this is the advantage of having at runtime and in generation time access to the meta model itself, right? In the M2 layer class, as to use the eCore reflection by using methods eClass to access the M3 layer and gain the type information of itself. The mechanism of reflection is an essential aspect when using generated code of metamodels in generic software. Well, I disagree slightly, but fine, at least on EMF. By using reflection, the program do not need to know the structure of an object. Instead, the parts can now be created by Metamodel runtime. So I really am trying not to be too critical here because these are different approaches, but reflection, use of reflection at runtime is seen as an essential property of the approach. In contrast, in MAST, we aim to avoid using reflection I wouldn't say at all costs, but as much as possible. So this is a very contrasting approach. Figure 3 depicts the reflection as it is defined in OMG's MOF standards. It consists of 3 classes: object, element, and factory. The object is the base class for every element in the metamodel. It provides the methods to access features of an object like properties or methods. The element extends the element metaclass of the UML. It provides the capability to access the upper meta level of a metamodel. This means when we create an instance of a class, we can access the description of the class via the getMetaClass method of the instance. Therefore, we can create the description to gain access, discover, and manipulate properties and methods of that instance. So as you can see here, you basically have the reflection world, and now you can start to do things like generate instances and so on dynamically, basically. The factory is a creator class for the metamodel. By merging the UML package to the MOF reflection package, the new elements are integrated into the resulting package, and the existing presumably one are combined with the new elements. This probably is a preprint, so there is a few typos. In the end, excerpt of the UML is extended by aspect reflection. So basically, yeah, this is a traditional approach where you can use reflection to do all sorts of things. We're not really that keen on this, so we just skim through all this. Why is it necessary to have an additional generator when it's also possible to use the transformation from UML to eCore and then use the MF for CPP generator like Eclipse does in our workflow? Clearly, this is a very important question. Our goal is to describe the structure and the behavior of software system with the domain-specific language. When converting a model from UML to eCore or MOF, the model is mapped to the elements of the meta model. Because there are no equivalent elements in the meta models for each element of the UML, the amount of elements is cut. Our generator does not map the elements of the meta model. So they're basically trying to explain that it didn't have enough time, effectively, to actually do all the work to bind everything together. Instead, it uses the old UML meta model for generation. The output of the C++ model representation is equal to the output of the EMF for CPP generator when converting the UML model to eCore before generation. The difference lies in the meta model package, which, in addition to the eCore model, also has a description of behaviors, constraints, and stereotypes. So I'm not entirely clear on what the rationale here is for this, but our goal is to describe the structure and behavior of such a system with a domain-specific language. When converting a model from UML to eCore or MOF, the model is mapped to the elements of the meta model. Because there is no equivalent elements in the meta models for each element of UML, the amount of elements is cut. Still not entirely clear, but it seems to be basically that their implementation is not complete, so we'll just leave it at that. Challenges. The UML Metamodel uses multiple inheritance extensively, so this is obviously a problem. To reduce the amount of duplicated code which accrues when implementing multiple inheritance with single inheritance, it is advantageous to use a programming language which supports the use of multiple inheritance, so C++ instead of Java. Figure 4, not that I'm a big fan of multiple inheritance, but there you are. Figure 4 depicts an excerpt of our inheritance hierarchy. So this is a typical UML sort of approach, UML elements, named elements. So in effect, these are all, this is a classic case of old style inheritance where we have these very fine-grained base classes with a little bit of functionality, then we merge them all together to obtain coarser-grained types, which was very popular in the 2000s. The figure shows a strict separation between interface definitions and specific implementation of the Metamodel elements. This has the main advantage to provide a public API to be used easily in other projects. It provides an encapsulation and increases the loose coupling. Otherwise, a compilation of the whole Metamodel will be necessary, which may take significant time. The separation of interface and implementation leads to a double diamond structure of the inheritance hierarchy. The virtual inheritance has to be used in C++ for this reason. Okay, it's classic C++ approach. This requires use of dynamic casting to go up and down the hierarchy. Not very nice. Other casts, like static or interpret casts, are illegal into invalid behavior caused by different pointer addresses. As a result, the computation time for necessary dynamic cost is much higher than multi-level inheritance. Yes, this is why we shouldn't really use this approach. C++ 11 standard provides many new syntax features to simplify programming. One of the main features is lambda expression. These expressions are type-safe, nameless functions used to simplify the implementation of factories, feature getters, and setters. Moreover, they allow the use of a similar syntax to the OMG specification. Figure 5 presents an example UML model representing an overview model of a so-called simulation-based application for planning and simulating wireless sensors in aircrafts. As an example. So we don't really need to get too hung up on this, but let's have a quick look. So a few classes here, components, a few positions, Mac, configuration. Okay, simple enough. The corresponding factory source code, which is generated by the UML for C++, generated is shown in listing 1. Where is listing 1? There we are. So it is a factory that uses a lambda to return a few things. And there's a map. Okay, fine. Just demonstrates using C++ 11, I guess. A similar method is used to implement the get, set, and invoke functions for the class object of the Moffer function package. Because C++ does not have a base type like the object in Java, these operations require a special return a parameter type for allowing both values and pointers as arguments. For this, we use the boost library. So basically, in order to simulate object, they use boost any, which can store any kind of type. The main disadvantage is the obvious lack of built-in polymorphism for this type. Due to the lack of polymorphic containers, a special list container is needed. Normally, what you tend to do for these sort of cases is to create your own object-based class, which is, I believe, what the other EMF package has done for C++. Until now, it's necessary to know the exact data type. This issue will change in the future progress. In further progress of development by introducing a polymorphic container. Memory management is a considerable concern for large models. To avoid memory leaks, std share pointer are a good solution. Is probably his best thing, because they automatically free memory when nobody is using an object anymore. A special case is the return to a self-reference. So you can start creating cycles, which is not applicable in every situation where self-references are needed and thus could cause failures. Moreover, the overhead of reference counting leads to an interesting computation time, compared to roll pointers. Thus, the UML model provides the needed information for the responsibility of the instantiated elements, making it easy to generate a safe memory management. The UML for CPP, we probably should have read the original for this. I wonder if it was written originally in Spanish. The UML for CPP thus only creates source code with raw pointer. Okay. By considering the composite feature of a property, the generated creates a correct memory management as it is modeled. So this is actually quite an interesting point. So because you know everything about the model, you can generate the optimal pointer management code. In fact, let's write a note here, because it's actually quite an important point. Memory management. Because the UML for CPP framework knows how the model is structured, it's keep using the old approach to spell checking. Is structured, it can generate efficient memory management code. This means using raw pointers is possible in a safe manner. In Dogen, we have a similar knowledge of the user code. We could also take advantage of this by introducing some kind of model level pointer class, which results in generating appropriate memory management code. So in other words, let's say for example you have a class that you know owns a pointer. So there is no need to make that pointer shared pointer. I mean, you know exactly the semantics of the use of that pointer, so you could encapsulate those semantics in the model itself, and you could say, well, this class always owns the pointer, so don't bother creating a shared pointer for it, just make sure you allocate on construction and deallocate on destruction, for instance. And then anyone using it must take into account the fact that the lifecycle of that pointer is bound to the owner of the pointer, and all of it is known by the model. So it's just something that we should keep in mind. We should probably just highlight all of this, because I think this is actually quite an interesting point that it's never occurred to us, funnily enough, even though we've been working on this sort of stuff for a while. And this is the reason why I need to read a lot of papers, really. Right, there we are then. So benchmark. This section presents results of a comparison between Java and C++ meta models generated by EMF and UML CPP. I mean, we're not entirely interested in this, so we're going to really skim through this section. Several important properties influencing the performance of practical application are compared, including creation time of model elements, time, effort to move model elements, comparison of model elements, amount of memory used. So general settings. A standard Windows PC, blah, is used to run the benchmarks. The Java benchmarks is running on a separate Java virtual machine. It is configured in a way that only one kernel is used, because current C++ implementation don't use multi-kernel functionality. Now, I don't think they mean multi-kernel, probably mean multi-threads, but the added startup time and size of the virtual machine itself is not considered in the following benchmarks. Which are also rather important, but it's a good point to make. We have a little model for the benchmark. The benchmarks use instances of a UML test class, which includes one attribute. That was the figure we just saw. The name of the class and the attribute is set. Different benchmarks use different amounts of instances for this test class. Creation benchmark. One thing that is actually relevant. We said that we're not really interested in this, but we could implement the test model in Dogen and perform similar benchmarks to compare the performance of an EMF-based kernel versus a mass-based kernel in Dogen. To analyze, the first benchmark compares the creation time and memory use of Java and C++ Metamodel implementations. Therefore, instances of the described test class are created in a loop varying between 10,000 and 100,000 instances. To analyze the influence of the Java garbage collector, the results of Java standard behavior and the results of a first grabber collection are compared additionally. The calculation is aggregated over 10 runs to average over the huge variation of computation times for the Java model Metamodel implementation. Figure 7 depicts the results of the first benchmark, right? So we don't really particularly care about this. The Java implementation, green and blue lines, need more creation time than C++ implementation. Moreover, the standard deviation of the creation time for Java implementation is significantly greater than C++. This is normal, especially the first result of the first run is significantly greater than the other creation times, of course, because you're warming up the JVM, which could be seen in the huge standard deviation of first creation time. This is caused by the first memory allocation of the Java exactly, and the fact that it reuses the already allocated but not needed memory for the next runs. The influence of a forced garbage collection, blue line, is less significant than expected. The creation time in C++ implementation is nearly linear and has a very small standard deviation. That's what we like about C++. The memory cleanup of the Java implementation is faster than C++, as expected for a huge amount of elements, because C++ deallocates the memory completely in contrast to Java. Model change and undo benchmark. To compare the performance with Java and C++ Metamodel implementation regarding model changes, the movement of a model elements are analyzed. What do we mean by movement? Therefore, 100,000 instances are described of the described test classes are created. All attributes are moved to one class. These operations are repeated 10 times again to calculate an average effort for the movement and undo operation. Okay, so presumably just deleting an attribute and moving it, copying it across somewhere else. The effort for traversing the model are analyzed by using a model comparison as well. For this purpose, 10,000 or 1,000 should I say, instances of the test class are created in two packages. All instances of the test class of one package are searched in the other package. This operation is also repeated 10 times to calculate the mean effort. Table 1 shows the results of these benchmarks. It becomes clear that Java implementation is much faster than C++ implementation. The movement operation is almost 4 times faster, and the model comparison is up to 100 times faster than the actual C++ implementation. The standard deviation of Java implementation is, however, relatively high. Okay? This unexpected behavior can be explained by the above mentioned need of dynamic cast by using the multi-level inheritance. Yes, the profiler confirmed that already known behavior of dynamic cast. Yep, with the higher inheritance hierarchy, more time is needed for dynamic cast operations. Possible changes to C++ implementation to improve the situation are discussed in section 5. Fine, we don't particularly care about that. Memory footprint. The hard disk memory use of the implementations are compared in table 1. The C++ implementation needs nearly 3 times more hard disk memory than the Java implementation. Okay, the reason for this behavior is probably the linking, of course, yeah, with several libraries including Qt and Boost. Okay, you don't know I need Qt. On the other hand, the value of the Java implementation does not contain the memory which is needed by the Java virtual machine. So it's trying to compare oranges with oranges, not very easy. The RAM use is measured by executing the benchmark in section 4.2. The maximum required memory is captured. As a result, the Java implementation requires approximately twice as much RAM as a C++ implementation. Of course, you're using the JVM, so difficult to compare apples with apples. In summary, the comparison of the generated Java and C++ implementation of the test class by using several benchmarks has shown divergent results. Okay, so on one hand, C++ implementation requires less memory than the Java implementation and is slightly faster in creating new instances. On the other hand, the current C++ implementation needs up to 100 times more time by using the model. This is caused by the need of dynamic cast and multi-level inheritance. To solve this issue, dynamic cast should be avoided by using interface realizations instead of multiple inheritance. So we have an advantage of being able to use multiple inheritance. What we do is very expensive. The implementation of the base classes has to be generated several times into the implementation of the derived classes then. This could be realized by changing the UML for CPP generator accordingly. This demonstrates one of the advantages of a model-based generative software development. Fine. An additional optimization steps to reduce time and memory consumption of the generated implementation. Model-based application for systems with after additional optimization steps to reduce time and memory consumption of the generated implementation. Model-based applications for systems with reduced memory consumption and storage capacity, such as embedded systems, could be realized. Might be worth a note here. So you're basically saying that there are some specific properties needed for smaller systems that are not quite catered for yet. As already mentioned in section 1, the generated C++ UML Metamodel could be used in several use cases. It is the base for the development of C++ based Metamodel tool family. By using our approach, it is possible to define, well, let's just for a note here, I guess. By using our approach, it is possible to define domain-specific languages for legacy software systems which do not have an explicit Metamodel right now. Okay, this is our second point. After adapting the legacy software system or legacy software to generate Metamodel, it is now easy to optimize and extend the language. Okay, I'm not entirely sure of that. Moreover, because the meta models are based on a standard metamodel, it is easy to transform it into another metamodel. I mean, this is all a bit theoretical, but in addition, it is possible to read and write models using XMI, which is a standard description of UML. Theoretically, it is possible to build a modeling toolchain based on C++ similar to the Eclipse modeling project, which has components for transformation, generation, and visualization. I'll give it a highlight here, I guess. As an example, we use the generation of UML model to define. How are we doing for time? 45 minutes. As an example, we use the generation of a UML model to define the visualization properties for attributes of a software system shown in Figure 5. Mambali Das. Let's have a look at Figure 5 actually. Okay, right. So just basically saying that we could visualize those classes. The stereotypes for visualization properties are defined by a profile diagram and are generated with the generator as well as the meta model where the stereotypes are applied to the classes. During runtime, a component analyzes the classes and visualizes the attribute values in a proper way. Moreover, it is possible to define constraints by using the standard OCL. By using the generated information of the constraints in the MetaModel package, it is possible to check the values of the attributes against the defined constraints during runtime. Another use case for C++ UML MetaModel is the model-based definition and execution of behavior, for instance by using activity diagrams. The OMG specifies a subset of the UML for execution, for executing activity diagrams, which is called FUML. Well, okay, we're now basically talking about the complete suite and all sorts of possibilities, and it's not exactly realistic, but it also contains a model-based description of the execution engine. Based on this model generator, the generator can create the execution engine. During runtime, the execution engine used the Metamodel package to retrieve the behavior elements and run the activity. There's quite a lot of typos here to make it a bit difficult to read. This paper presented an EMF-like UML generator for C++. The workflow structure and some implementation challenges of the UML C++ generator are presented. Examples have proven the practical usability of the resulting C++ implementations. The comparison generated Java and C++ implementations of models by using several benchmarks with regards to resource use as shown diverging results. The presented UML for CPP generator can be used to create C++ code representations of eCore. Well, this is probably worth highlighting. The eCore metamodel, the UML metamodel, and models based on these metamodels. This provides the basis for creating C++ based execution engines, transformation engines, OCL validation tools, and other model-based applications which are subject to future developments. So lots, a world of possibilities here. Because the generator is a first prototype, it still needs some further development. Features like the notification framework, proxies, and references to other models are partially implemented or still missing. So worth a note here as well. That's perhaps a green. And so there you go. Okay. So this is supported by German grant. Okay, so all in all, what to say about this paper? So it's interesting. I hope that they've continued work on this. Probably will have a look to make sure this project is still going. The main takeaway from this is that we could create a new masked kernel, and that masked kernel could target EMF. Now this is actually useful because we would then be able to create. So there's several ways in which this could be useful. There's the injection sort of way in which we want to take an eCore model. We like to inject that into Dogen, but then actually just use that to generate code as we use any model, any UML model, like Jäger, for example. In which case, the models you generate are not EMF models. In other words, you're still using the masked kernel, and you've got no reflection, none of those things. The second approach is you use an EMF model for injection, but you use the EMF kernel, so that the runtime model then binds to the EMF which then allows you to do the sort of the usual things of reflection and so forth. So in fact, as I say this, I think probably should go back and update the notes. So this approach is useful in two ways. To create an EMF injector. For this we could use the eCore codes to parse EMF models and then adapt these into Dogen as we do with any other injector type. The generated code will look like regular Dogen codes, and it will make use of the masked kernel. This is just using eCore as a bridge into Dogen. So this is kind of a half-baked use of I mean, it's very useful because if you've already got models, you probably just want to generate those models. So it's not entirely useless, but it's just not a complete vision. The second approach is to have a EMF stroke eCore. I don't think we got the same spelling of eCore twice. Kernel, which generates codes that is proper EMF. Well, how should I describe this? Which has the full functionality of eCore, including runtime dynamic aspects. So for this we rely on UML for CPP as a PDM. And so these are two interesting approaches. We need to understand whether any of this will be a requirement for the work we're currently doing, really. But nevertheless, this is the point of these papers, is to open your horizons. So, okay, we're reading 1 hour, so I guess we should call it a day. It's a very interesting paper. Well, we shall see next week.